Hello, students. A very good afternoon. My name is Ravi Ranjan Kumar, and I welcome you all in this second session of rotational motion. In today's class, we will be covering torque, equilibrium of rigid bodies. Then we will look at the concept of toppling, and then we will talk about angular momentum as well. So, without losing any time, let's start the discussion. So let me share my screen with you people. Okay, so let's start the discussion of torque. Torque is basically ability of a force to rotate a body. Okay, so for example, uh, if we have a hinged door, let's say this door is free to rotate about this axis, okay, and we want to rotate this door using some force. So apart from the magnitude of force, the other things which are going to be decisive in rotating this door over here is where we must apply that force and at what angle we are applying that force. Let's say, for example, the point of application of the force is here, say, and say we are applying some force in this direction. Okay, so this is F, and let's say the position vector of this point with respect to the axis of rotation is R. Okay, so now, like, the torque would be defined as tau is equal to R cross F. Okay, and when we will be writing its magnitude over here, it will be equal to Rf sine theta. Now look at the expression of this torque over here. It is this expression includes not only the magnitude of force, but it also includes that what is the distance or point of application of force with respect to the axis, and also it includes that what is the angle between the position vector and the force vector over here. So here this physical quantity which we have defined to measure the capability of a force to rotate a body, okay, includes all these information of force, position and angle. Okay, and now this expression in vector form can be written also as, let's say, for example, the position vector in component form is represented as xi cap plus yj cap plus zk cap. Okay, and force vector is represented as fxi cap plus fyj cap plus fzk cap, and here you see fx, fy and fz are the component of force along x, y and z axis respectively. So in that case, the expression for torque will look like this. That would be I, J, K, X, Y and Z, and Fx, Fy and Fz over here. So this expression is in determinant form. Okay, so now let's look at this figure again over here. So I was saying that this is the capability of a force to rotate the body. Now you see, if we resolve this force into two mutually perpendicular direction, one direction is along the force, along the radius vector or position vector, and the another direction is the direction perpendicular to it, and this angle is given to us as theta. So this component is going to be f parallel, you can say, that would be equal to f cos theta, and this component is f perpendicular that will be equal to F sine theta. So now just by looking, you can say that the F parallel or F cos theta component will not be responsible to rotate the door. If the force is in this direction, the door will be not rotating at all. So the force, the component of force which would be responsible for rotating, all that matters is the component which is perpendicular to the r vector. So F perpendicular. Okay, so that is why in the expression of torque, we are having the sine component. So in that case, this torque over here can also be represented as r times F perpendicular. Okay, we are not interested in the parallel component of force here. In order to find out the magnitude of torque, we only are interested in what is the perpendicular component of force. Another way of looking at it is this also. Let me choose another color pen. We can divide this position vector into two mutually perpendicular components as well. So let's say this direction here is along F, and this is the direction perpendicular to F. So this radius vector or position vector can be resolved into two mutually perpendicular components. One would be this, that would be along F, and the another component would be perpendicular to F. So this we can write it as R parallel, and this we can write it as r perpendicular. And since this angle is theta, this thing is going to be r cos theta, and r perpendicular is going to be r sine theta. So this expression can be viewed as F multiplied with r sine theta. So another way to represent the magnitude of torque is also r perpendicular into F. So you can have you can use any of these three expressions for the magnitude of torque. Either you can use RF sine theta, or RF perpendicular, or R perpendicular into F. This is how you can find out the magnitude of torque. And when we are talking about the direction of torque would be along R cross F, and the direction of R cross F can be used using right hand thumb rule. That means if you draw the vector r, okay, and vector f, and let's say the angle between them is theta, and you curl the finger of your right hand along r to f, okay, the vector r to f, then the direction of thumb, which would be outward, the direction of thumb that would be inward in this case, will be giving you the direction of torque. So if the curls of finger is clockwise, then the direction of torque would be inward. And if the direction of r cross f, the direction of curl of finger, is anti-clockwise, then the direction of torque would be outward over here. So we have talked about the direction as well as the magnitude of torque. Okay, so let's take one very simple question, okay, and try to learn like at which condition, which of these formula in RF sine theta, or RF perpendicular, or R perpendicular into F, which would be applicable easily in what case. Let's take one simple example. So let's say this is a horizontal surface, and from point O, a particle of mass m is projected with initial velocity u, making an angle theta with the horizontal. So obviously its motion is going to be projectile motion, like this. This is the path it is going to follow. So the question is, when the particle is at its topmost point, let's say here, okay, when the particle is at its topmost point, what would be the torque experienced by the particle due to gravity about point O? So whenever we are asking about torque, few things we need to understand. Like, we are trying to find out torque experienced by what, due to what, and about which axis. So here we are trying to find out torque on this particle, and we are trying to find out the torque due to the weight. So its weight is going to be vertically downward, which is equal to mg. Okay, and we are trying to find out the torque due to mg, okay, about an axis passing through O. So this here is going to be the position vector. This is r. So obviously the magnitude of torque is given by rf sine theta, or you can say r into f perpendicular, or r perpendicular into f. So which formula, using which formula would be more suitable in this case? So for example, if we plan to use this formula rf sine theta, so okay, the magnitude of f is very known to us, so but we need to calculate additionally the magnitude of r, and we need to calculate the value of sine theta also. If we use formula rf perpendicular, so r we need to calculate first, and f is given, but we need to calculate the perpendicular component of force, which is not directly given. So using this formula will also be not very appropriate over here. But looking at this third formula, r perpendicular into f, so magnitude of force is known to you, so only we need to look into the perpendicular component of the position vector. So that seems easy for us. Let me use other color pen. So this is the vector r, so we can resolve this r into two mutually perpendicular components. So this component would be r perpendicular. Okay, so r perpendicular, you see, would be nothing but half of the range. And range, the formula for range is nothing but u square sine 2 theta by g, and that divided by 2 would be r perpendicular. Now we can very well substitute this result over here, and the magnitude of f is mg. So that would be simple, uh, u square sine 2 theta by 2g into mg, and that would be your answer. Obviously um, here g etc will be getting cancelled. Okay, so this is the one of the question. So now we have learned how to find out the torque due to a single force. Now let's try to look into torque due to multiple forces on a body. So let's say we have a body, and say this is the axis of rotation, and this is say point O, and this body is experiencing many forces at different points. So let's say this is point 1, and its position vector with respect to 1 is O is r1, and it is experiencing some force f1. This is point 2, so its position vector is r2, and it is experiencing force some f2 over here. Similarly, other forces. Okay, so net torque, if we wish to find out the net torque, that would be the vector sum of individual torques due to each and every force. So that can be written as summation of ri cross fi. So this is how we are going to find out the torque. Okay, so in order to find out the magnitude of the net torque over here, the magnitude of the net torque over here, okay, in this simplified case, when the direction of torque is either inward to the plane or outward to the plane, writing down the magnitude of this torque becomes easier. Only we need to figure out that due to a given force, the torque will be trying to rotate the body either clockwise or anti-clockwise. So clockwise means the torque would be inward, and anti-clockwise means the torque would be outward. So in that case, either uh, like if we take the outward direction as positive, either the magnitude, either the torque, we can say vectorially it would be positive or negative. For example, here in this case, if we are trying to write the torque and taking the sign of outward direction as positive, means anti-clockwise we are taking positive. So here torque due to F1. So torque due to F1, you can very clearly see in this diagram, has capability of rotating this body in clockwise direction, and its magnitude would be nothing but you can say um, R1 F1 sine theta 1 would be its magnitude. But since we have taken outward direction and positive, and this torque is inward, we will take it with negative sign. And similarly, you can see that the F2 has the capability of rotating this body in anti-clockwise direction. So its magnitude would be R2 F2 sine theta 2. And since it is anti-clockwise, so the direction of torque would be outward, which we have taken as positive, so we will be having this as plus sign. So this is how we can write the magnitude of torque in this simplified case, when the torque will be either outward or inward. Okay, so basically you can say only one dimensional problem, that is. Okay, so this is the net torque, and obviously the direction, this torque would be in outward direction, direction outward to the plane over here. So in all this discussion, we have been seeing that the calculation of torque, or simply torque, the definition of torque depends upon the axis of rotation, or the point about which we are finding torque. So if we try to find out torque about one axis, and if we try to find about torque about another axis, those two quantities may or may not be the same. So if we try to relate the net torque due to multiple forces about two different points, what would be that relationships? Let's try to look. Okay, so let's say we have a body, and we have 2 points, let's say point A and point B, and let's say here this is a position I, and here we have applied some force Fi. So the position vector of I with respect to A would be nothing but R I A, you can say, and the position vector of I with respect to B would be nothing but R I B. Okay, and obviously this vector we can write it as RBA, that is position vector of B with respect to A. Okay, so how can we relate? Like for example, if we try to write down the torque about B, so torque about B simply can be written as tau B is equal to R, sorry, uh, RIB cross Fi. So that is torque about B. And torque about A, and summation of that, and torque about A can be written as summation of RIA cross Fi. Okay, so we want to have a relationship between tau B and tau A over here. So let's modify the expression of tau A. So RIA can definitely be written as RIA can definitely be written as uh, RIB minus RAB. Okay, cross Fi. And this, when we will expand, this will become RIB cross Fi plus RAB, we will be writing it as minus RAB, we will be writing it as RBA cross RBA is a constant, so it will come out summation of Fi. So this quantity over here, this quantity over here is nothing but torque about point B. So tau B plus RBA cross, and this quantity is nothing but the net force over here. So tau A is equal to tau B plus RBA cross F. So this is the relation. If we know torque about torque about a point B, we will be able to find out the torque about any other point A using this relationship over here. Now, closely looking at this relationship, this gives us a wonderful result. That special case I must write. So if the net force acting on the body, if F is equal to 0, so this the second term of this expression will become a null vector. So that will give us tau A is equal to tau B. So that means if the net force acting on a system or net force acting on a body is equal to 0, so the torque will not depend upon the choice of point. It will be same about each and every axis. So in fact the choice of point does not matter in this case. So it is a very very wonderful result. So whenever we are into a situation that the net force acting on the body is equal to 0, we can write the equation of torque about any axis we please. Okay, whichever axis will be most convenient to us in order to write the equation of torque, we will be using that axis. Okay, to solve a given problem in order to save our effort. Okay, so this is a very very important result. Okay, the next concept I want to talk about is something called point of application of force. Point of application of force. Let's say this is a body and multiple forces are acting on this body. Let's say point 1, some F1 is acting, point 2, some F2 is acting, point 3, some F3 is acting. Different forces are acting on this body. So these forces are going to produce some torque about some axis O. Okay, so the torque about this axis can be written as tau, can be net torque, can be written as summation of Ri cross Fi. Now I wish to uh, have a situation when all these forces I want to replace it by one single net force. Okay, so I want to replace it with one single force, the net force. Obviously this F I am saying, F is summation of all the forces. But where should this force be applied? Let's say this is applied at point P such that it produces the same net torque. Then the position vector of this point P, or the position of point P, will be known as point of application of force. So that same torque we can have using this point of application where we will be applying the net force. So this tau can also be written as Rp cross net F net, or simply summation of Fi. So if we equate these two relationship, like Rp cross summation of Fi or net force must be equal to summation of Ri cross Fi. So solving this equation, this will give you the position vector of point P, which would be the point of application of force. That is nothing but point of application of force. Let's take a very, very simple example in order to find out the point of application of force. Very simple example I am going to take. So let's say we have a simple straight rod and we are say applying 20 Newton force here, and we are applying 30 Newton force here, and we are applying say 50 Newton force here. Let's say this is the midpoint and length of this rod is L. Okay. So multiple forces we are applying on this rod, and we want to replace all these forces with a single net force. Okay. Such that it will be having same effect as the combination of all these forces. Okay, so what would be the point of application of this force over here? So let's say this point is A, and this point is B, and this point is C. So obviously the net force is will be 50 plus 20, 70 minus 30. That would be 70 minus 30, 40 Newton. That would be in vertically upward direction. So somewhere we need to apply 40 Newton force, and we want to find out the position, like where on this rod this point P will be located. So for that, let's try to find out torque about O. Let's say torque about torque about A, let's say we try to find out. Okay, in both these cases, and this torque, we will equate them as equal. So torque about point A, so 20 Newton force is not going to apply any torque about point A because it is passing through the same point A. And torque due to 30 Newton would be simply uh, R perpendicular into F. So R perpendicular is going to be this distance, and this distance is nothing but L by 2 into F, and the magnitude of force is 30 Newton. And since this is in clockwise direction, okay, so we will use negative sign as we are taking the anti-clockwise or outward direction to be positive. So this is the torque due to 30 Newton. And then we will be having torque due to 50 Newton force, and that would be its arm is basically L, so L into 50, and that will be equal to torque here. So let's say this distance is X from A, so that would be equal to X into 40. So we can very well calculate. So 40X is going to be 50 minus 15, that is going to be 35L. So that would be X, I think you will be getting as 7L by 8 over here. So the point of application would be located at a distance of 7L by 8 from A over here. So this is how you can find out the point of application of force. Now let's learn about the concept of center of gravity. Center of gravity is a term which is often confused as center of mass. But let me tell you, these two quantities are not essentially same. They are different. Okay. So center of gravity is nothing but this is point of application of gravity. This is point of application of gravity. Now you see, let's say you have a body with a continuous mass distribution, and it would be made up of a small elements, dm everywhere. It would be continuously distributed, and all these elements will be experiencing the weight of their own. Let's say for example dmg and DMG, etc. So if you calculate the net force, this will turn out to be, net force would be somewhere mg. In order to have same effect, okay, of torque, we need to apply at a given point. Net force would be effectively be applied at one point, and that point of application here in this case would be termed as center of gravity over here. So net torque, if we would like to write this torque would be nothing but r cross f. So you can write it as r cross dm times g, that is the force acting on each element, and the integral of this thing, since this is a continuous mass distribution, this will be giving you the net torque. And since we have located as center of gravity, so what we can say, that will be also be equal to r cog, that is position vector of center of gravity, cross mg over here. Okay, so solving this relationship, that will give us the expression for center position of center of gravity over here. We will be looking at one simple case. If g is uniform, g is constant, so if g is constant, solving this equation number 1 over here, this part, the left hand side of this equation over here, so this will turn out to be r cross or r dm cross g. We can take this g out of integration sign, and that would be simply equal to r cog cross mg over here. Now this quantity, in the previous chapter of center of mass, we have defined the center of mass, the position of center of mass. So this thing inside the bracket is nothing but rcom into mrcom cross g it will become, and that would be equal to rcog cross mg over here. So just by comparing the left hand side and the right hand side of this equation, we can very well see that if g is constant, then only RCOM will be equivalent to RCOG. So this is a wonderful result for us. So as long as we can make sure that we are working in uniform gravitational field, the center of mass of the body, we can use it as center of gravity. Okay. So whenever some weight is acting over a body, we can effectively use for calculation the center of gravity where all the weight will be concentrated. So that thing we will be using frequently in problem solving. So we have talked a little bit about torque, and improvising over that, like we can establish the condition for the equilibrium of rigid body. A rigid body is said to be in equilibrium if net force acting on the body is equal to 0 and the net torque acting on this body is equal to 0 as well. So now looking at this condition, we have already said that the net force acting on the body is equal to 0. So when we are saying that net torque acting on the body is equal to 0, we do not necessarily need to mention that we are calculating the net torque about which axis and we are equating it to equal to 0, because the net force acting on it is equal to 0. So net torque will be equal to 0 about any axis. The choice of axis does not matter as long as net force acting on the system is equal to 0. So saying that, let's move on to solving some question of equilibrium of a rigid body. So let me open that file for you. So equilibrium of rigid body we will be talking about. So a few simple question we have chosen. So this is the question over here. So there is a wall. There is a vertical rigid wall over which we have placed a block and forcing it or pressing it over the block using some force F. Okay, and the mass of this block is m and its width is b. The line of this force is passing through the center of this block over here. This c is the center of mass of this block. So in uniform gravitational field, this c will also acting like center of gravity. So let's draw the free body diagram of this. Its weight would be effectively passing through or acting at center of gravity, so that is basically mg. Okay, so since that block we have to keep that in equilibrium, so there would be some friction acting on that in order to balance this mg. So this is F, and there would be some normal acting on that body as well. Okay, so obviously the normal would be in rightward direction, but right now we don't know that what would be the line of like effective normal would be passing through what point. So we will draw it later. So first of all, so like normal, let's say, would be somewhere here. Okay, we don't know, we are interested in finding out this distance d. Okay, so where this normal is acting. So since this is in equilibrium, net force acting on this block is equal to 0. So considering the net force along vertical as well as horizontal direction, N is equal to F by equating the horizontal forces we have got, and F is equal to mg by equating vertical forces we have got. So that is equation number 1, and that is equation number 2. Now our next job is to balance the torque. The net torque acting on this body must be equal to 0. So we should choose over here like what would be the where should we choose our axis so that our calculation becomes easy. So for example, if we plan to write the equation of torque about this point C over here, the torque due to F and torque due to mg about point C is going to be equal to 0. Okay, so looking at point C, there would be torque due to this friction that would be clockwise in nature. So in order to balance that clockwise torque due to friction, we need the torque due to normal in anti-clockwise direction, and that could be possible if only this normal gets shifted uh, below C. So in that case, the torque due to friction, which would be force into arm, so this is F, and the arm would be this quantity over here, so that is going to be B by 2, and that must be equal to the anti-clockwise torque due to normal, so that would be N into D over here. So here we are able to get the value of D, so that is nothing but FB by 2n over here. And before that we have already established that the value of F is equal to mg, so that will become mgb, and the value of normal is capital F. So answer is D is equal to mgb by 2f over here. So that is the first question, where we are having line of action of normal that has been shifted below the point C here. So now let's look into the another example very quickly. So this is the problem of leaning ladder. So here we are having a ladder which leans against a smooth wall. This wall here is smooth. Okay, but this surface, the coefficient of friction mu is given, so this floor is rough. Okay, and we have to find out the smallest angle theta. We have to find out the smallest angle theta such that the ladder does not slip. Okay, so how can we find out that? So at the critical value of theta, we will be having the limiting condition for friction, means friction will be just able to contain the relative motion of this point with respect to ground. So now let's draw the free body diagram of that. So here this ladder is in contact with the rough surface. Okay, so there would be some normal on it that would be in vertically upward direction, and this point will have a tendency to slip in rightward direction. So there would be a opposing static friction that would be in this direction, let's say F1, and here at this surface, okay, there is no friction, so there would be only some normal, so that would be equal to N2, and apart from that the weight would be effectively acting at center of gravity, which here would be coinciding with center of mass, and that would be mg. So I have drawn all the forces acting on this body over here. So this, and looking at the force balance, first of all, horizontal force balance will give us F1 is equal to N2, that is say equation number 1, and vertical force balance will give us N1 is equal to mg over here. So that is equation number 2. Okay, so now we want to write the equation of torque. Net torque is equal to 0. So which axis we must choose? So let's say this point is A, and this point is B, and this point is C. So the intelligent way or the wise way of doing it, like we must choose the axis such that the torque due to as many forces becomes 0. Okay, so this, if we choose to write the equation of net torque about point A, torque due to N1 and F1 will both become equal to 0, and we will be left up with writing torque only due to mg and N2, which would be easier. Okay, so when we will be writing net torque about O, about A, let's say. So torque due to N2 will be in clockwise direction. So torque due to N2 will be N2 times R perpendicular, and R perpendicular would be this distance over here, and let's say the length of this rod is L. So this is going to be simply L sine theta. So that is torque due to N2, which is in clockwise direction, and that would be balanced by the torque due to mg, which is in anti-clockwise direction. So mg will be producing, the magnitude of force is mg, and this here would be arm of this force. So that is going to be L by 2 cos theta over here. So what we have got here is N2 is equal to, when we will be cancelled, so N2 is equal to, we have got mg by 2 tan theta. Okay, so that is the value of F1 as well. So for critical condition, we can say, let me erase that part here. So here we can say that for critical condition we need to have F1 must be less than mu n1. So F1 we have already calculated, so that is mg by 2 tan theta, and that has to be less than equal to mu n1, and n1 is equal to mg over here. Okay, so what we can say that tan theta would be greater than equal to 1 by 2 mu. So here we can have the minimum value of tan theta, that would be equal to 1 by 2 mu. So that is a simple question over here. Now let's move on to the another question. Okay, so see, so let's first read the question. Let me minimize this so that we can see this whole thing. So the left rod, so this is the situation. We are having rod BC and rod AC, and the left rod extend infinitesimally beyond the end of right rod. So this is extended a little bit beyond the right rod over here, and the coefficient of friction between the two rods is mu, and both sticks have same mass per unit length, and end A and B on the ground are hinged. These two ends are hinged. So this rod can rotate about A and B. So we have to find out the minimum value of theta, this minimum value of theta for which the rod do not fall. Okay, so looking at this position, now let me again maximize this diagram. So looking at this position over here, so they at point C, these two rods are in contact with each other. So they will be applying contact forces with normal and friction over each other. So let's say the force experienced by C, that normal would be in this direction, and see see this normal would be in this direction, and the right rod will have a tendency to slide down. So it will experience the right, so the normal on the left rod would be in this direction, the friction acting on this would be in this direction, that is N, and the friction acting on this rod will be in this direction, that is you can say F over here. So this action reaction pair of normal and friction I have drawn over both the rods. So if we balance torque about point B in this case on the rod BC, okay, so in the rod BC, the force acting R, say that is its weight, that is its weight, you can say the weight, let's say linear mass density of these two rods are equal, and that is equal to lambda. So let's say point like from B to A over here, so this length is L, so this is going to be, this length is going to be L cos theta, and this length is going to be L sin theta over here. So its weight can be written as lambda L sin theta into G. And similarly, the weight of another rod that would be acting at its center of gravity, that would be lambda L G cos theta over here. So if we will balance torque about point B on rod AC, so there would be no torque due to this friction over here, because that is passing through point B. So the torque due to normal would be simply normal times length, which is L sin theta, and that must be equal to torque due to its weight. So that is lambda L sin theta into G, and that multiplied with its arm. So its arm would be, this is lambda L sin theta by 2. So lambda L sin theta by 2, uh, and sine component of that, so that would be equal to sine square theta. So L sine theta and L sine theta will be getting cancelled. Okay, so what we will be getting here is normal would be equal to lambda square L sine square theta by G over here. So that would be the normal. And similarly, when we will be writing the equation of torque about 1 2 I have missed over here, so that is 2. So similarly about A, when we will be writing torque about torque on this rod, that will be torque due to friction would be F, and that multiplied would be L cos theta. So FL cos theta would be nothing but lambda L cos theta into G is the force, and its arm would be L cos theta by 2, and its cos component, so that would be equal to 2. So simply F you can write it as so sorry, here there would be no lambda, so that would be lambda L cos square theta. So G would be here as well, sorry. So lambda L cos theta, cos square theta into G by 2. So from here F we can equate it uh, as F should be less than mu n. Okay, so substituting the value of F and n over here, what we can say after solving, we will be getting tan square theta that must be greater than 1 by mu. So the minimum value of tan theta here will be 1 by root mu, you can say. So that is this question. So we are really running short of time. So let's discuss two problems, two good problems over here quickly. So let me minimize this diagram a little bit. So look at this situation here. So what we are having, a uniform right angle triangular lamina that is suspended from the ceiling with the help of three strings, and the plane of lamina is horizontal. This is a triangular lamina. This is a triangular lamina and it is horizontal and it is suspended by three strings having tension TA, TB and TC. Okay. Which of the following option has to correct? So option A, B and C, A, B, C, D are trying to compare between TA, TB and TC in their magnitudes over here. So how are we going to comment on this thing? So let me redraw this diagram for us. Okay, so let's say this is the right angle triangle and we are having uh, this as B, and let's say this is A and this as C. AB is given to us as 3 meter, BC is 4 meter and this is 5 meter. So we are looking the top view of this thing, let's say. So here the tension would be acting in vertically upward direction, so that would be TB, and tension would be acting here in vertically upward direction, that is TC, and the tension would be acting in vertically upward direction, that would be TA over here. Okay, and apart from that, this triangular lamina will be experiencing its weight effectively at its center of gravity, and that would be somewhere here. Okay, and it will be experiencing a force that would be in inward direction, that is say mg over here. And here center of gravity, as you know, will be coinciding with center of mass of this triangular lamina, which would be nothing but the centroid over here. So in order to compare the magnitude of TA, TB and TC, let's try to have equation of torque about an axis passing through A and B. So if we have chosen this as axis, torque due to TA and TB will become 0. Okay, because R perpendicular for these cases due to TA and TB will become 0. So only there will be torque due to mg and torque due to TC about line AB over here. So now you see, let's say if this thing is some h. So using geometry, uh, h by 3, the line of application of mg would be at distance h by 3 from AB over here. So and since this is in equilibrium, torque due to mg and torque due to TC will be cancelling each other. So we can say that TC into h will be equal to mg into h by 3, you can say mg into h by 3. So that gives us TC is equal to mg by 3. And similarly, we can find out TA, TB, TA and TB. In order to find out TA, we need to balance torque about line BC. And in order to find out TB, we need to balance torque about line AC. In all these cases, TA as well as TB as well as TC, both all will turn out to be equal to mg by 3. So here we can say TA and TB will be equal to TC, which collectively will be equal to mg by 3. So that we can say that this option where we are having TA is equal to TB is equal to TC, that would be the right option over here. So let's quickly move on to the next question. And one similar question I want to discuss here is, let me minimize this diagram. So here we are having three threads of length L1, L2, L3 are fastened, okay, through a common vertex over here. Okay, and this is a triangular lamina. Okay, which is homogeneous, and it is having weight. The other end of the threads are fastened to a common point. Okay, and the lengths of thread are L1, L2 and L3. Assume all the threads are taut and the plate is in equilibrium. So this is the diagram here which we are looking at. So that is suspended using three threads of different lengths L1, L2 and L3, such that the triangular lamina ABC is has a horizontal orientation when it is in equilibrium. So now we are required to comment on these options A, B, C, and D. So the first option is tension in the threads are proportional to their lengths, and option C is tension in the threads are inversely proportional to their length. Okay, so basically tension in the thread is either proportional to their length or inversely proportional to their length. We need to figure out in this question. And the another thing is they are asking like whether in option B vector sum of tension in the string at the plate and the weight of the plate is equal to 0. So that definitely seems to be correct, because since this triangular plate is in equilibrium, so the net force acting on this must be equal to 0. So let's say this is T1, this is T2, all these would be vectors, and this would be T3, and apart from that W is acting. So the net force would be T1 plus T2 plus T3 plus its weight, and the vector sum of all these is going to be a null vector over here. So definitely the option B is correct. And now about option D, they are asking the center of mass of the plate is at the centroid. Okay, so center of mass of the plate is definitely at centroid. So this part of the question is this part of the statement is true, and it should be below the point of suspension, and that also seems to be true, because if we balance the torque about the point of suspension, T1, T2, and T3 all are passing through this point of suspension. So T1, T2, T3 are not going to create any torque about the point of suspension. So the only force left is W. So since the net torque about the point of suspension is going to be 0, so torque due to its weight is also going to be 0. Torque only due to its weight is also going to be equal to 0, because torque due to T1, T2, T3 are 0 as well. So that means the arm of the force would be arm of the weight with respect to this point will be 0 as well. So that means W will be passing through this point. W will pass through P. So this is, let's say, point P. So now the coming to the very first part, like whether the tension would be proportional to its length or inversely proportional to length. Let's quickly do this problem. So say, let me redraw this diagram over here. Let me redraw this diagram. So let's say this is the triangular lamina, that is A, B, C, say, and this is the point of suspension. Okay, so if we draw the vertical line passing through point of suspension over here, this is going to pass through the center of gravity, G. Okay, so this is a vertical line, and if we join P with A, so this is going to form a right angle triangle. Okay, and TA will be acting in along this line. Okay, and let's say if this angle is theta, okay, so the vertical component of this TA, there would be two component, obviously one would be horizontal and the another would be vertical. So this component is going to be TA cos theta. Okay, and the weight would be in vertically downward direction, that would be W. And again, like in previous question, if we balance torque about point BC, the torque due to TA would be TA cos theta, and say this thing would be h by 3, and this perpendicular distance would be h using the geometry. So ta cos theta into h would be equal to w into h by 3. So like in previous question, here we will be getting ta cos theta a, rather say ta cos theta a, that will be equal to w by 3. So ta cos theta a, we can say, and cos theta a, we can look in this right angle triangle over here. So cos theta would be nothing but this quantity, like this is centroid. So let's say that is ag. So and that would be you can say, or this height would be whatever, let's say this height is some capital H. So uh, cos theta would be nothing but this capital H, and that's the length of this is LA. So that would be H by LA over here, and that would be equal to W by 3. So here you can say that TA by LA is a constant. So that means TA would be directly proportional to LA. So the tension in the string would be the directly proportional to its length. So that option would be correct in this case. So basically the time management of this class wouldn't have been proper. Okay, so we are left with the discussion of toppling as well as conservation of uh, angular momentum. So in the next class we will be talking about these two concepts, and basically we would be trying to do some less problems in order to save some time for the theory. So this is the end of today's session. Thank you very much.